Still going? Okay, felt like I did something funny. So we skipped this page. I'm not exactly sure that we need to spend too much time on it at this point because again, like I've been telling you, I just want to tell you just enough so I don't tire you out. So this page is all about the origin of voltage and the word potential. Sometimes people will say voltage and sometimes they'll say potential. And I don't know that you really need to know the difference right now. But let's just jump into this. So this is a positive charge. This is the positive plate. This is a negative plate. Do you see why the positive charge is going to the right? So this is the unit we just did, basically. This is the electric field. This pushes it to the right. And I think I talked about this as a warm-up one time. You can imagine, or hopefully you can imagine, if I grabbed this thing and I pushed it over to here, it wouldn't want to do that, but that would be like compressing a spring. And if I let go, it could fly back this way. So basically, by pushing a positive charge to the left, I'm storing potential energy in it. And then by letting it go, flying back to the right, that potential energy is changing into kinetic energy. So let's just let's do a little bit of this, but I'm not going to do all of it. Where in the diagram would the positive charge have the greatest potential energy? The answer is on the left side. So just like the ball has the most potential energy up here on the hill because gravity's pulling it downhill, and you store potential energy by pushing something sort of against gravity, this electric field pushes the thing to the right, so I store energy in things by pushing charges to the left. Now, if this were an electron, I'd push it the other way and it would shoot back to the left. But anyway, if the positive Q charge were released to travel from A to B, what would happen to the potential energy as it went from here to there? Would it increase or decrease? Potential energy, stored energy in this. Decrease, because pushing it to the left stores up energy, and then I let go, whew, decreases. So what would happen to the kinetic energy? It would increase. It would go faster. Just as electric field is force per unit of charge, electric potential, you'll hear that a few times. We won't really talk about it much. Mostly we'll talk about voltage, is electric potential energy per unit of charge. So what this is saying, well, maybe I'll just use this example. It's not the same thing as electric potential energy. So at the same potential, let's say 2 joules per coulomb. If this is at a potential of 2 joules per coulomb, we don't know how many joules it has. Depends on how many coulombs of charge it has. So if it is a positive 1 coulomb charge, then it's going to have 2 joules of potential energy. If it's a positive 3 coulomb charge, how many joules does it have? It's got 6. It's got 2 joules for every coulomb. So if it has 3 coulombs, it's going to have 2 joules for each of those, which means 6 altogether. So if I held it here and I let it fall to 0, which would be like letting the ball roll to the bottom of the hill, then I would release, this much energy or this much energy. And this is analogous to having a ping pong ball or a light ball at the top of the hill, letting it roll down, and then have a bowling ball or a cannonball, put that at the top of the hill, let it roll down. The bowling ball is more like this. It's got a lot more mass, so it has more energy per kilogram. Or sorry, no. The cannonball. Did I say bowling ball? Okay. Cannonball, bowling ball. The big ball would have more mass, so it would have more potential energy. And a lighter ball, like a ping pong ball, would have less mass, so it would have less potential energy. So anyway, potential is not the same as potential energy. It's a ratio of charge to potential energy, or potential energy to charge. And potential is not the same as voltage. Voltage is potential difference. So it's like this. If this ball gets to the ground, it loses a certain amount of potential energy. If this ball gets to here and it has, let's just say it has 0 potential energy, 0 joules left of potential energy, then it's lost all of its potential. Here's what voltage is, though. I measure the potential of this here, and I get, I'm just going to say, 2 joules per coulomb. And then I measure the potential of it here, and I get 1.5 joules per coulomb. What voltage is? It's the difference between those two. So what would the voltage be? How many joules per coulomb? 0.5. All right. Now, I'm not going to spend time on that really anymore, but it's just when you think of voltage, you can think of it as pressure. You can just imagine like a pushing force pushing this thing across. You could also imagine it as potential energy that can be unleashed. And you're just comparing basically two different parts on the hill, right here and right here, and you're thinking about the potential energy difference between those two places. That's what's driving all of these circuits that we're going to be doing. So let me just jump to a diagram that might explain what I'm getting at. Let's see. Like in this. So we're going to be doing this later on, so don't mark it up. This is the last page. All right, can you see it? Do you have one? Yeah. So I'm on the last page. So this voltage, remember I said it's like a pump? So basically, just think of it as PSI for a second, pounds per square inch, instead of volts. And this side, this is the positive side, this is the high pressure side, 18 PSI. And then over here is 0 PSI. And this is going to pump stuff out here into this area and pump it across here and pump it through this resistor and pump it through this resistor and then all the way back. So the analogy I was making with a car tire is this is sort of like the gauge pressure. The inside of a car tire, my car tires are 50.7 PSI, and the air around them is 14.7 PSI. And the gauge, if I put a little pressure gauge on there, it's going to say 36 PSI. Because that's the difference between the pressure inside and the pressure outside. So this 18 and this 0, that's the pressure difference. That's the difference in potential energy between here and here. This might have 1,018 PSI, and this might have 1,000 PSI. It's just telling us basically somewhere over here has 18 joules for every coulomb more of potential energy than when it gets to here. So this is like a hill that represents a height, so that if you have a little positive charge that's 1 coulomb, that's going to have 18 joules of potential energy more than when it gets to the bottom of the hill right over here, where it's going to have 0 coulombs per 0 joules per coulomb. It gets to there. And if you measure the voltage between here and here, they're not going to be the same, because as the charge moves through here, it's going to lose some of its potential energy going through this resistor. This could be a fan or a light bulb or whatever. So it's going to have less potential energy here. And then it spends some more energy in this, and then it gets back to 0. And then it gets pumped up and more energy is added to it, and then it goes through here again. All right, so that's enough for the first page. That was more than enough. In fact, I think I've depleted a good bit of your willingness to pay attention. So that's the key. This is the A5. This is the handout I was working on. Your handout has very little. Let's not even bother with this right now. Stuff at the bottom. We could do that later. Current. Let's just do a tiny bit. I'm going to resist the urge to really write more. Current is defined to be the rate at which, does anybody know what's flowing with current? What's going through that circuit? What? Waves. Now, when you get more advanced, maybe it's waves, but for now, the things that are moving through. Yes, electrons. So we picture it as positive charge, but it's charge. So at the rate at which charge flows. And the equation for this, I don't know why it's I. Maybe I looked it up once. I can't remember. I is the symbol for current, and it's Q, which is charge, divided by time. So charge over time. So it's not necessarily a speed. It's just like if you have some flow this way and you've got a little gate across, it's counting how many coulombs go across every second. The unit is, does anybody know the unit? What? Coulombs per second is equivalent to that. So 1 ampere is what it is. It's 1 coulomb per second. And it's the, oops, sorry, let me write that more neatly. I don't want to go too fast, be too messy. 1 ampere. And if you talk to people about it, if you're talking to an electrician, nobody really says amperes. They say what? Amps. And oddly, the symbol, I don't have a space for it, but the symbol is A. So A is the symbol for amps, which is the unit for current. The symbol for current is I, and I don't know why. Sounds like a poem. Guess maybe it is. All right. So that's enough for that. That's all you need to know about current for now. I think so. I'm pretty sure. Yeah. It's capital A, so it must be. Yeah. You can look up Sir Ampere. I bet there was one. So this next page, we did it in the other class. I killed him. We're not going to do it. So let's skip this for now. Basically, it's just talking about Ben Franklin. It's throwing out there that we know we do current totally backward because we pretend that current flows from positive to negative, and it doesn't. It's actually negative charges going the other way. So this is important. We need to do Ohm's law. Let's just jump right down to the middle. Ohm's law can be written 3 different ways. My favorite one is I equals V over R. This is the one I shared with you last class, because this is the way it makes the most sense. I, you've got V, you've got R. What's I the symbol for? We just did this one. Current. So this is current. This is the amount of flow. What's V the symbol for? I didn't write it down, but I think you can guess. This is volts. This volts is sort of the pressure that's pushing things. It's the potential energy that charges have that drives them through, just like potential energy of a ball on a hill rolls it down. And then R, what's that? Resistance. So this is my favorite way to write it if you're trying to make sense of it. This is flow. Do you get more flow if you have more volts? Yeah, more pressure pushes more flow. Do you get more flow if you have more resistance? No. More resistance, you get less flow. So current's directly proportional to volts or pressure, and inversely proportional to resistance. And I don't think this is super important, but you can also write it like, if I want to solve it for R, it would be R equals what? V over I. And then this graph makes a little bit of sense. I'm going to do 3 different situations. So these, let's say these represent 3 different circuits. Which one has the most resistance? Top one, middle one, or bottom one? So if you look at this, if you have, let's say, this much voltage right here, then you have this much current. With this one, if you have this much voltage, you have that much current. So if you have a situation where not very much voltage, not very much pressure gives you a lot of flow, is there much resistance? No. So this would be high resistance here. You can have a huge amount of voltage here, but you only get a small amount of current. But if I went all the way out until I hit this, that you'd have a whole bunch of current. Also, what's the slope of these lines? What is the slope? Yeah, it's V over I. So it's rise over run is resistance. So I'm just going to write slope. The slope of this graph equals resistance. So this is representing a high resistance circuit, and this is representing a low resistance circuit. The units for resistance, you wouldn't have guessed this, but I think I told you. Remember what they are? Ohms. And I don't think they're called that because the symbol is an omega. I think that's just pure coincidence. But maybe not. Capital omega, yeah. Maybe they tried that for every unit, and that's the only one where it actually panned out for them. All right, so skipping again. Let's skip forward a little bit to power. Power is the next thing. These are all just random pieces so we can do stuff that I think is interesting. So the next page, it's page 6. Some of you might not have page numbers. Some of you do. So power, let's not do this. Let's come back. The other class didn't know what was there, but I think we can do it. You remember the units for power from earlier in the year? Watts. The unit for power is watt. And 1 watt is 1 joule per coulomb. I don't know why I wrote it like that. 1 joule per coulomb. And power is the blank of energy use or energy consumption. Do you know what goes there? Measurement. Measurement of what aspect of energy use? How much energy you use?
Oh, efficiency.
Not efficiency. That's efficiency.
Yeah, absolutely.
Joules per coulomb. Oh, wait. Ugh, I'm so sorry. I didn't screw up until just now. You know what? Yeah. What is it really? 1 joule per what? Second. Yeah. I'm sorry. Joules per second. Disgusted myself. So anyway, so knowing that if power is joules per second, does that give you any ideas here? Sort of rate. It's a rate. So it's how much energy is the it's the ratio of the amount of energy used to the amount of time. And you don't have to write this down, but volts is joules per coulomb. That's the potential energy per unit of charge. And current is coulombs per second. And if you take joules per coulomb and you multiply it by coulombs per second, then you get joules per second. So power is volts times amps, or voltage times current. So that's one way to calculate power. And I'm going to write a couple of other useful kinds of ways to do it down here. And I'm going to bring in the fact over on the side that this is Ohm's law, I equals V over R. So if I take P equals VI, which is the power formula, and I substitute in V over R for I, what do I get? Yeah, so you can also do V squared over R. That's one of the equivalent formulas for power. And if I rearrange this to get V equals IR, and then I substitute IR in for V, then what do we have? I squared R. So any of those will work. In some situations, if you have current and you have resistance, you can get power. If you have voltage and resistance, you can get power. If you have voltage and current, you can get power. And we're like little butterflies stopping on flowers. We're going to move on to the next flower. This is a big one. Okay, we're going to gorge ourselves here for a while. Here and the next page. And then move on. So the purpose of this is going to be some review from what we did last time, and then adding that to what we're doing today, the new stuff. I'm going to do a series circuit here and a parallel circuit and write down some rules as we go. And pretty much after After you know that, you can start figuring out circuits, and it's just going to take a lot of practice to get good at it. So this is going to be a series circuit. Those of you who are here, can you picture what that's going to look like? It's going to be a line of resistors. So over here on the left, I think I'm just going to do it, I'll do it like I've done it in the past. So this plate, usually the wide plate right here, this is positive, and the less wide plate is negative. So that's a battery or something, and it's driving current out of this positive. I'm just going to put a little note. Current comes out this way. And it's going to go through this wire, and it's going to go through, let me make this angle down a little bit, 2 resistors. There's R2, or sorry, R1, and this will be R2. You can put them wherever you want. These squiggly deals I'm doing, there's no particular number of squigglies that you have to have. You can make as many squigglies there as you want to. So this is R1, this is R2, and what makes these in a series? All current flows through every resistor. So that's kind of the definition of series. This is a 12-volt battery, tells us here, and we're given the resistances of these things. R1 is 2 ohms, and R2 is 4 ohms. The typical kind of stuff you have to figure out is what is the voltage, current, resistance, and power for every aspect of this circuit. So the battery and the current coming out of it, that represents the total current and the total voltage for this circuit. We can find total power and we can find total resistance. And then for each of these resistors, we can get the total voltage, total current, total power, total resistance. And what we're doing now is learning the rules for how to do that. We've already learned the rule for this. I taught you the rule for total resistance the other day. So the total resistance for series, how do you do it? If you have a resistor of 2 ohms and a resistor of 4 ohms and they're in series, what's the, add them up. So you don't have to write this, but in general, the generic formula is R1 plus R2 plus R3, and so on and so forth. So in this case, the total resistance for this whole circuit is 2 ohms plus 4 ohms equals 6 ohms. Okay, current. Find the current. So we're going to find the current coming out of here, and then we're going to find the current going through here, and then we're going to find the current going through there. Current's easy for this one. Why? It's series, which means how does the current going through each of these and the battery compare? It's the same. It's like the river flows out here, the whole river goes through here. The whole river goes through there. The whole river goes through there. It's all the same. So the rule is total current, or I should have written total I because that would have been less to write, equals I1 equals I2 equals I3, so on and so forth. But how do I get the total current? I know the total voltage. I know the total resistance. Yes, I've got my special tool, Ohm's law. So current equals, I'm going to write total, equals the total voltage over the total resistance. You don't really have to write these little totes here if you don't want to, but whatever it is you're trying to find the current of, you need to find the voltage drop across that thing. Like, what's the change in potential energy across here? What's the change in potential energy across here? They might be different for these different places. But for the total one, it's going to be 12 volts over 6 ohms, because that's the total one that we just found. So what's the answer? 2 watts. Very good. Correct answer. 2 amps. So that's the total current. So what's the current through this resistor? 2 amps. And that resistor, 2 amps. So these are all 2 amps. And there should be 2 R's in current. Voltage drops. This is where it gets kind of tricky. So what I want to find is the voltage drop, like total voltage drop. I want to find the voltage drop here and the voltage drop here. Voltage, remember I told you, is like pressure. And this is like 0 psi over here, 12 psi, and then pressure pushes something across here. We're going to get down to less pressure on the other side. And then as that remaining pressure pushes something across here, we're going to get to even less pressure. In fact, we need to get to 0. Let's see, what can we do? I think we can just use Ohm's law here. So we know the amps through this, and we know the resistance of this, so we can use Ohm's law to get the voltage. So let's do that first. Let's do voltage of resistor 1. It's going to be I1R1. So the current going through resistor 1 right here is 2 amps, because everything has a current of 2 amps. And the resistance of resistor 1 is 2 ohms. So I get 4 somethings. What should the units be? Volts. So 4 volts of like sort of potential energy difference between a charge here and the charge that's passed by. It's lost some coulombs, or sorry, from some joules per coulomb. And if I do the same thing for the second resistor, it's going to be the number of amps, 2 amps, times the number of ohms. How many ohms? 4 ohms. So we get 8 volts. And if we do the total, it's going to be the number of amps, which is the same as the individual resistors, times the total resistance, which is 6 ohms, which equals 12 volts. So comparing the total to the individual voltages, what's the relationship? Yeah. So V total equals sum of individual voltages. And that should make sense. It's like if you think of it as pressures, you start out with 12 psi more here, you drop to less, you drop back to 0. So these 2 drops have to add up to whatever that is, and then you pump back up again. Power. Remember the formula for power? It's joules per second, but that doesn't really help for the formula here. What's that? There are 3 different ones. You could do, is it V squared over R? Or you could do I squared R? Or you could do my favorite, which is VI. Any of those will work. I'm going to use VI because I like it the best. And I'll do the power for each of these. So what's your guess? If we compare the entire amount of power, the entire number of watts used by this whole circuit to the number of watts used by this resistor and the number of watts used by this resistor, are they all going to be the same, or are these going to add up to the total? That's kind of the 2 patterns we're going to get. Add up to the total. It only makes sense. It's like if your house is using 1 kilowatt right now, then that means you've probably got something that's using maybe 0.2 kilowatts and something else is using 0.8 kilowatts, and they're adding up. So that is the way it works with power, no matter what kind of a circuit you have. But I'll just go through it. So the power for the first resistor is the voltage, and the voltage for the first resistor is 4 volts multiplied by the current, and the current through everything is 2 amps. So we get 8 watts. And the power through the second resistor is the voltage. I'm using this one. Second resistor has 8 volts, and the current through everything is 2 amps. So that's 16 watts. And then if I do the entire circuit total, it's going to be 12 volts times 2 amps. I get 24 watts. So yeah, they add up to them. So the rule for power consumed by individual resistors and overall is P total equals sum of P individual. I keep trying to come up with more concise ways to write things. If you need to get up and take a break, because this is a painful class, and you can do that, I understand. This is always a long slog, but I feel like teaching all this stuff together, yeah, we can. But you're going to miss something, so hurry back. Just getting all this stuff out together is the best way to do it, because then we can start using it. Okay, same thing except parallel. So I'm going to draw the same circuit as before with a 12-volt battery, and R1 is going to be 2 ohms, R2 is going to be 4 ohms, but it's going to be parallel. Can you picture how it's going to be different, those of you who are here? So I'll put the battery in the same position. This is still going to be a 12-volt battery. This is still the positive terminal. This is still the negative terminal. The current still goes this way. But the current doesn't have to go through both resistors. It's going to have 2 paths. It can go through this resistor. This will be R1, which is 2 ohms. Or it can go over here and go through that resistor, which is R2, which is 4 ohms. With the other one, I felt like we could just use formulas and deduce everything on the page. There's one thing on here that's sort of a mental leap. You're just going to have to believe me on this. So total resistance, the rule for doing this, we went over this last class. I'll write this down. I can show why for anybody who wasn't here if you want at some point. But the easiest way to write the formula is to write 1 over the total resistance equals 1 over the first resistor plus 1 over the second resistor's resistance plus 1 over the third resistor's resistance. And you just keep following that pattern. So if we do 1 over 2 ohms plus 1 over 4 ohms, that should equal 1 over the total. So in this case, 1 over R total equals 1 over 2 ohms plus 1 over 4 ohms. So we've got 2/4 plus 1/4 equals 3 over 4 ohms. So if 3 over 4 ohms equals 1 over R, what does R equal? 4/3. 4/3 ohm. And I think I'll just leave it in that form. I'll leave it as 4/3 of an ohm. So that's the total resistance of the whole thing. So the whole circuit has less resistance than each of the resistors. This has 2 resistors. Overall, the circuit has less resistance than that. Does that make sense? It might not at first glance make sense because it seems like adding more resistors should give you more resistance. But what we've done is we've added paths. So if you just have this, you only have this path to go through. You're going to have a certain amount of flow. And by opening up this path, however clogged, you're going to get more flow. And if you have more flow and more current, that means you have less resistance. So now we can find the currents. Find the current for the individual and overall currents, or currents in parallel circuit. This is the one where we have to take a mental leap. Does anybody know how to do this? How would I get the overall current for the circuit? Actually, the overall current's easy. It's the individual ones that are tricky. Use the overall R, and, yeah, V. So it's just this formula, I equals V over R. So if I use the total voltage drop divided by the total resistance, then I'll get the total current. And that's 12 volts over 4/3 of an ohm. 9. And what would the units be? Amps. Okay, so we can do that for that one because we know the voltage of this one. But what's the voltage drop across this one? And what's the voltage drop across that one? So this is where the pressure analogy that I've been over before is kind of helpful. If you think of this as being a series of pipes, and you think of this as a pump, and it pumps things up to 12 psi here, and this is all one big cavernous pipe right up here, where air can flow easily. There's nothing impeding it between here and all over there. I could draw it looking like, actually, let me go back to the warm-up where I did draw it looking like this. Here, like this. So if the pressure is 20 psi right here, what's it going to be all through here? 20 psi. And if this gives a voltage of 12 psi. So what that means is the pressure over here is 8. And the difference, the voltage is the difference between these two. So we've got 20 psi all around over here, and we've got 8 psi all over here. And this pump increases the pressure by 12 psi. The important thing is the pressure difference across D and H and E and I and F and J are all what? 12. So minus 12. So you go from 20 down to 12 here. You go from 20 to 12 there. So the voltage drop in a parallel circuit like this is the same as the source. So that's an important rule that we'll actually write down when we get to D. So this is kind of out of order. But I'm just going to use that for these other ones. So I for the first resistor is going to be 12 volts over 2 ohms. And that gives me 6 amps. And really, at this point, if you're clever, you can just deduce what I2 is going to be. Does anybody know what I2 is going to be without doing this? Don't do 12 divided by that. Yeah. What's another way of knowing that this is going to be 3 amps other than 12 divided by 4? Yeah. So this is 9 amps of flow right here, and 6 of it went this way. So this is going to be the rest of it. Or we could do it this way. We could say there's 12 volts, and you divide that by 4 ohms, and you get 3 amps. So one of the rules for individual and overall currents in parallel, if you look at these individual currents and you look at the overall current, what's the comparison? Like, how do they relate? Are they the same or they add up? Yeah. So the rule is the I total equals the sum of I individual. The rule for those. All these rules, these are going to help you later on, and you'll internalize them. Voltage drop in each resistor, I've already given you the rule. The rule is V total for a series or for a parallel circuit is the same as each of the voltage drops. Equals V1 equals V2 equals V3, and on and on. So in this particular case, V total equals 12 volts, and that equals all these other ones, V1 and V2. And we're almost done, and then we'll take a little tiny break and we'll do some puzzles. Some bad puzzles, but we'll fix them. The first one's bad, it needs to be fixed. Calculate the power dissipated by each resistor. Power, my favorite formula is VI. You can use any formula you want. But I want to do the total. The total would be the total voltage, which is 12 volts, multiplied by the total amount of current, which is how much? 9 amps. And that gives us 108 watts. And the power dissipated by the first resistor is going to be how many volts? How many volts are across this one. Yep, 12 across everything. So 12 volts multiplied by its current, which is 6 amps, and that's 72 watts. So you could do this again for the second resistor, or you could figure out the wattage how. Yeah, 108 minus 72 is 36, and that's equal to 12 volts times 3 amps. So either way works. Done with that.